Okay, another application for Faraday's law, other than the examples that we just shared together, is the transformer. I think all of you had studied the transformer in one way or another before, and the transformer looks like what's shown here, where we have a primary inductor, we have a core, like a high permeability magnetic material, ferromagnetic material, and a secondary core. When we apply a time varying current, I primary, in the primary core, it will induce flux, and the flux will flow into the core. The flux doesn't escape to the air, as we discussed this before, because the resistance or reluctance of air is much higher than the reluctance of the core, and that's why we are creating the transformer's core from very high permeability magnetic material, ferromagnetic material. So this core is like directing the flux to have the highest possible link to the secondary. When the flux is coupled to the secondary through the core, the secondary inductor will carry an induced current, because this is a time varying flux going into the secondary core. This is very direct application of Faraday's law. The current generated in the secondary inductor or core is such that it opposes the primary generated flux, so that the flux, or the magnetic motive force of the primary minus the magnetic motive force of the secondary equal reluctance multiplied by flux. We know all that the reluctance equals the length of the core, the total length of the core, divided by permeability and cross section. For an ideal transformer, we would say that the core is a perfect magnetic material with mu equal to infinity, so that the right hand side of this equation will equal 0. So we'll have the number of turns of the primary multiplied by its current equals the number of turns of the secondary multiplied by its current. So we know all how to do this. The ratio of primary current to secondary current is the transpose, or the inverse of secondary number of turns divided by the primary number of turns. We know that the V will equal minus N d phi by dt. So from Faraday's law, we have the potential of VB equal minus N d phi by dt. So Faraday's law, electromotive force potential equal d phi by dt, and phi of course equal b dot ds, and n is the number of turns. So it's very similar to the example we just solved. So the primary potential, the voltage between the two terminals of the primary, equal minus n b d phi by dt. Secondary is very similar but with ns, so that we can find the ratio between the primary voltage and secondary voltage, which is the same ratio as the primary number of turns divided by the secondary number of turns. So here the current is transformed with the opposite of the ratio of primary to second. The potential is transformed by the ratio of primary to second. If we calculated the resistance of the primary inductor, which is VB divided by IP, and we just do the math. We know that VB equal NB divided by NS multiplied by VS, IB equal NS divided by NB multiplied by IS. We'll find that the ratio of primary resistance, the effective resistance of the primary, equal N primary divided by NS square of the effective resistance of the load here. So the current here at the load equal IS multiplied by equal VS divided by IS, so that we can say that transformer is also transforming RL into like RB. So, and if we are dealing with like a complex load, not just resistive, it will be ZL and ZB instead. So the transformer, we can see that the transformer is transforming voltage, current, and impedance. So it can be up conversion for voltage, so it is a down conversion for current, and it is sort of like the square up conversion of inductance or resistance. Sorry, impedance or resistance. So now, how the model of real transformer looks like. This is the original relations that we have. The flux equal NB IB minus NS IS. The reluctance is now not zero, so it is something like some numbers. So the potential at the primary equal NB d phi by dt, and here like the negative sign, it depends on how we like define the positive and negative, and like how the inductors of the primary and secondary are winded. It depends on the direction of winding. We can like put negative or positive depending on the direction of winding and the definition of what is positive and what is negative. So V1 equal NB d phi by dt, and from this relation here, this is phi, and this is the reluctance equal L divided by mu s. Again, the reluctance equal L divided by mu s. So in this case, we just like substitute here, we get a expression for the primary voltage, and we can just like relate this to like the models that we have. The potential, we know that the voltage equals the self-inductance minus di secondary by dt of the mutual inductance, the coupling between the two inductors. So this is from magnetic circuit and this is from electric circuit. We can just by comparing the two expressions, we can find the expression for the primary, the self-inductance of the primary, and the mutual inductance between the primary and secondary. And of course, LSP is the same as LPS because of the reciprocity. So again, this is from magnetic circuit, this is from the expression from electric circuit. Just mapping the two terms, we can come up with an expression for the self-inductance and an expression for the mutual inductance for the transformer. And this would be like sort of like a more realistic model for the transformer. We would like to know what is the meaning or what those elements represent. So the mutual coupling between the two inductors is related to like a factor k that is less than 1, and this one is a little bit slight than one because there is some flux leakage, and this is sort of like represented by x1 and x2. So those are representing the sort of the leakage, how much flux goes out of the core. Those inductors at the inductors at the primary side and secondary sides are made of conductors. Those conductors are not perfect, they have some losses, and these losses are presented by R1 and R2. So R1 and R2 represent the losses in the core of, in the coils of the primary and secondary inductors. So in the core there will be some losses, and these losses we're gonna like talk about it. It's like hysteresis losses and eddy current losses. In magnetic material lectures, I think lecture number 4, we talked about the hysteresis losses. When we magnetize and demagnetize, or magnetize and change the direction of magnetization, there will be some losses into this, and it's called like hysteresis or residual losses. This is represented by our core. There is also a losses that we're going to just discuss it after this slide. It's called the eddy current losses, and the eddy current losses can be reduced significantly by laminated core, as we're going to see and exercise. So the hysteresis nonlinearity is presented by XC. So this model here takes the like leakage of the flux into consideration, X1 and X2, losses in the conductor coil of the primary and secondary, R1 and R2, the losses in the core, magnetic losses in the core, RC, and the nonlinearity of the ferromagnetic material, which is XC. So now let us talk about the meaning of eddy current. So for this transformer here, the cross section is like sort of like a rectangular cross section. We have here, we have some fields that's inside the core that's going in this direction, and these fields are varying with time. So look into this conductor, which is the, okay, let me bring back my pointer. Okay, so if this is the core, there is a magnetic flux going in this direction, and this magnetic flux is varying with time. If you consider any of those loops, you will find that there is a time varying magnetic flux penetrating this loop, so there is an EMF that is circulating the current in this direction. And because the conductor is like a material with a limited conductivity, there will be some losses, like ohmic losses, along this like path, along this path, along this path. So the current will be circulating in this direction. This is a cross section here. If we are cutting at this level, the cross section will look like this, and there is circulating current. This current is called eddy current. So it's a losses or a heating up for this core material. One very common way to like solve for this problem is to create the core as laminated layers. So I think many of us had seen a transformer with laminated layer for the core, and between each layer and the other there is like a wax or like insulator. So the time varying magnetic field or magnetic flux will be penetrating a much smaller area. You remember that the EMF E dot dl, the EMF is proportional to partial phi partial t, and phi equal B, the magnetic flux, multiplied by S. So by reducing the surface that the field penetrate, the EMF will be smaller and the eddy current will be very small. Compared to this case, consider the current at this outer ring or outer virtual path. The penetration or the flux is very large, so large current is flowing here and causing a lot of losses and heating. And of course, heating would cause the transformer to be burned or something like that. So avoiding it is a must, and one very common way to avoid this eddy current loss is the laminated iron core, like this shape here. Okay, let us study more about eddy current. And let us watch one video that is explaining this.
Hi. So, what is electromagnetic braking? What are eddy currents? Well, today I'm going to discuss both, and to start off I'm going to give you a small demonstration first. I have here a small stick with a piece of copper attached to it. Here I have a fairly strong rare earth magnet, and as you can see, the magnet itself is not attracted to the metal. If I start swinging it, you can see it moves fairly freely and continues to swing for a reasonably length of time. But what if I now actually start it to swing and then bring my magnet really close to it without touching? As you can see, the piece of metal slows down reasonably quickly. So what's going on? Well, that's all about eddy currents, which leads us to our understanding of electromagnetic braking.
This is a very important part talking about the electric
So here
brake.
we have the situation that you've just seen. So I have a magnet and I have this piece of metal which is going to pass through the magnetic field. Now we have here the magnet where the north pole is basically on our side of this metal strip and the south pole would be on the other side. Now that's difficult for us to actually see what's going on, so it's helpful if we then also have another view where we can see from the top perspective. So this motion of the metal strip here corresponds to the motion of the metal strip here. And what I've done here is just give you a representative of the north pole and the south pole. Now I know in the section that you saw earlier I had a single magnet, but what I'm demonstrating here is going to apply equally as well. First of all, we know that when we move this metal through the actual magnetic field, we're going to have the metal move across magnetic field lines. Now, according to this, those magnetic field lines look something like this. And I'm going to just use a yellow color here. They're going to be moving from the North Pole to the South Pole. And of course, they should be nice and perpendicular. But of course, outside that, they would arc a little bit over. So what we're getting here is that we're getting a fairly constant magnetic field here, but as we move out this way and move out this way, the magnetic field changes, or more specifically, the magnetic flux density changes. And so the magnetic flux is also changing beyond the actual magnets at this point here. So the question is what occurs here? Well, we have this metal strip that is a conductor and it's moving in a changing magnetic flux. So it's increasing in flux as it enters here and it's decreasing in flux as it leaves here. Now, what happens in the metal is a production of small eddy currents, and the best way to show you what the eddy current looks like is the eddy current would occur somewhere in front and somewhere behind, because we're going to get a changing flux in front and behind the magnet here. But the question is what is the direction of these eddy currents that are taking place? And to help us understand that, we need to remind ourselves of Lenz's law, and Lenz's law says that the polarity of an induced current will always be such that it opposes the thing that changes it. And so how are we going to work that out? Well, if we're going to get an eddy current over here, it's going to produce a magnetic field that opposes the motion. So in the case that is right here where my mouse pointer is, this section is moving away from these magnets. So what we want to do is generate a small magnet, so to speak, that opposes that motion. Now it's moving away, so we want some sort of a magnet here that is actually attractive. So it would look a bit like this. Now this is not a physical magnet, but it's just supposed to represent the magnetic field that we want here. So if this is moving away, then we want a little magnet here that we want to attract back to that direction. Similarly speaking, if this is moving towards these magnets over here, we want a little eddy current here that opposes it, so we want it to repel. So it's going to look something like this. And again, if we have this trying to enter the magnetic field, there's going to be a repulsion here. Now, if you want to now work out the direction of the current, now that we have the view of what these little magnets look like, all we need to now is to use our right hand grip rule. And so our right hand grip rule will be such that if I grab a magnet and grab it in the direction where the thumb is pointing towards the North Pole, my fingers represent the flow of current in that coil. So as you can see, my fingers are curling up and out. So from a side perspective over here, then what does that look like? Well, that's going to look like a current that is going to go in that direction. Similarly speaking, if I now look at the reverse here, I'm using my right hand grip rule and I place that over to point my arrow points where the North Pole is. You can see my fingers are curling in the opposite direction. And so again, if you're looking from this perspective over like this direction, which is what we were really wanting, you can see that this direction is in the counterclockwise or anti-clockwise direction. And so there you have it. You have two eddy currents forming on either side of my magnet as a result of the fact that the metal is moving through the coil to produce these eddy currents. Now, this is a little different though if I were to use the magnets. If I were to move the magnets, then the magnets obviously will be relatively moving in the opposing direction, so the reverse would happen. You can try that yourself and think that through as a way of understanding this. Because of the fact that these eddy currents oppose the motion, we have in essence a braking effect. And of course the braking effect means that we often refer to this as electromagnetic braking. A number of industrial applications use this by simply moving magnets near metals that are moving and thereby slowing down that metal due to the production of eddy currents.
So now let us look for like sort of like an application for this, like to visualize it as an experiment with this video.
Welcome to my video presentation for the project for ECE470 vehicle electronics. For this project, I have built a magnetic braking system that is being currently experimented with in certain vehicles. And it works on the principle of eddy currents. And as you can see, there's an aluminum rotor here, and it being aluminum is non-ferromagnetic. And on the end of this representative brake pedal are some very strong rare earth magnets. And as you can see, if I hold it over here, there's no attraction between it and the rotor. The rotor spins on this axle, which is driven by this electric motor, which in turn is powered by this representative brake pedal. Now obviously this wouldn't be how it's set up in an actual vehicle, but this is just to demonstrate a purpose. Now, if I press the brake pedal, the accelerator pedal, the wheel will start to turn. Once it gets up to speed, Alright, and as you can tell, it's spinning pretty fast and it's not slowing down anytime soon, but if I move this arm over here, it stops it almost instantly. And the reason why this works is because the magnetism in these magnets here, when it's moved over this piece of aluminum, you effectively have a moving magnetic field, which causes current to flow in the rotor as it's spinning. And that flowing current then in turn causes an equal and opposite magnetic field of these magnets, which slows or causes a dragging effect, which slows down the rotor. Now, there's a couple of problems associated with this and actually using it in a vehicle. And one being simply that at slow speeds, it doesn't stop the rotor from turning, or it won't hold it in one fixed position. So to use this system in an actual vehicle, you'd have to have some sort of mechanical clamping force to hold the rotor while the vehicle is sitting still. Okay, that concludes my video presentation. Thank you for watching.
I hope that those two videos give you a good view about the explanation and view of one of the application of eddy currents. There is other applications of eddy currents, for example the magnetic furnace, where we are using magnetic current to we need the current to flow heavily on the metal so that it can be used for heating or for melting the metal up.